Welcome back to today's deep dive. If you are the kind of learner who, really loves finding profound insights in hyper-specific technical details, you're definitely in the right place today.
Oh, absolutely. This is exactly the kind of stuff we love to unpack.
Right. So today we are looking at a really fascinating snippet of content. It's basically a snapshot from a developer's notes. And just to be clear, we are focusing entirely on the core logic here. We aren't worried about who wrote it or what website it's hosted on.
Right, just the pure mechanics of the problem they're solving.
Exactly. So the premise is this developer is working on part 101 of a programming project. And they're building this in Haskell, which is a programming language. They are making a text parser.
A text parser, yeah.
And they already have this system in place that perfectly identifies chapter headers. But now they have a new mission. They need to upgrade the system so it can recognize a broader structural container, which is a volume header.
Which, adding a volume on top of a chapter, it sounds like a pretty minor tweak. But it actually forces a huge fundamental shift in how the program comprehends the text.
Wait, really? Why is that such a huge shift?
Well, because you are moving from a simple flat list to a multi-layered hierarchy.
Okay, I see. So before we look at how the developer actually solved this, let's talk about the machinery at play here. Like, what does a parser actually do?
That's a good place to start.
Because to help you, the listener, visualize this, I always think of a parser like a highly automated factory assembly line.
Oh, I like that.
Yeah. You feed this raw, continuous ribbon of material, the text in at one end, and the first machine on the line chops that ribbon into little pieces. It says, here's a word, here's a space, here's a number.
Right, and that chopping process technically is called lexical analysis or tokenization.
Tokenization, okay.
Yeah. The parser is converting the raw characters into tokens, which are just the smallest meaningful units of data.
But just chopping it up isn't enough, right? The next machine have to actually sort those pieces. It looks at the tokens and says, the token for the word chapter is right next to a number token. So I'll put these together into a chapter box.
Exactly. And that is known as syntactic analysis. It takes that flat conveyor belt of pieces and builds a structure, usually called an abstract syntax tree.
An abstract syntax tree.
Yeah, an AST. And this is where that jump from chapters to volumes gets really complicated.
How so?
Because when the system only knew about chapters, that tree was super flat. A book was just, chapter 1, chapter 2, chapter 3.
Right.
But a volume is a container of chapters. So by adding a volume header, you totally alter the shape of the tree. The parser now has to keep track of a broader state.
Oh, I get it. It has to know, I am currently inside volume 2, so the next chapter 1 I see belongs to volume 2.
Precisely. It's building a much more complex map of the text.
Yeah.
And doing this in Haskell adds a whole other layer of difficulty.
Yeah, I've heard Haskell isn't exactly a fast and loose language.
No, not at all. It's a purely functional language with a super rigorous, statically typed system.
Okay, what does that actually mean for the developer?
In plain English, it means the compiler, the program that translates the code, is incredibly pedantic. In languages like Python, you can kind of hack a structure together, and it'll try to guess what you mean.
It's a bit more forgiving.
Exactly. But Haskell does not guess. If you tell it a book is made of chapters and then suddenly try to shove a volume in there without explicitly defining how a volume works, the program just flat out refuses to run.
It demands total structural integrity.
Absolutely from the ground up. You have to mathematically prove to the system that a volume can hold chapters.
Okay, so knowing a volume exists conceptually is just step one.
Yeah.
But that doesn't actually tell the factory line how to find the volume header in that endless ribbon of text. And this is where the source notes get super interesting to me. To build that new boundary, the developer didn't just invent a new rulebook from scratch. The notes explicitly say the only significant change required was extracting one specific pre-existing function.
Just one function. And it was a function that was previously buried deep inside the chapter parsing logic.
Yeah, and the name of this function is so revealing. It's called is Chinese numeral or digit.
It's such a specific name.
So specific. They extracted this function so they could reuse it for both chapters and volumes. But, I have to push back a little here. Let's unpack this. Is moving one highly specific function really a massive architectural change?
It really is.
Because it's like, I don't know, realizing you don't need a second Swiss Army knife for the kitchen. You just take the one from the garage and put it in a shared drawer. Why wouldn't they just write a brand new rule specifically for volumes?
Well, because writing a new rule introduces a massive risk to the whole system.
Really? Just writing a new rule.
Yeah. Think about the mechanics of extracting a function. When that numeral logic was locked inside the chapter parser, it was entirely local. It was tied exclusively to the concept of a chapter.
Right.
By extracting it, the developer is performing an act of abstraction. They are separating identifying numbers from the where the chapter header.
Oh, I see. They're isolating the variables.
Exactly. And the implications for stability are huge. By elevating this to a global level, you establish a universal law for the entire program. You're telling the system, hey, from now on, whether you're looking for a chapter, a volume, or whatever, this is the one and only way we define a number.
And let's look at the complexity hiding in that function name. Is Chinese numeral or digit? It's not just looking for like an Arabic numeral, a 1 or a 2.
Right.
It's also looking for Chinese characters that represent numbers. That tells us a lot about the data they're parsing, right?
Oh. It sure does. It suggests they are dealing with complex, culturally specific text, maybe translated documents or web novels. You could have chapter 1 with a digit, and then chapter 1 using the Chinese character for 1.
And to a machine, an Arabic digit and a Chinese character have absolutely nothing in common.
Nothing at all. They're completely different numeric codes in the background. The computer doesn't magically know they mean the same thing.
The developer has to explicitly map out every single valid character.
Exactly. Now imagine if they hadn't extracted this function. What if they just wrote a second completely separate rule for volume?
It's almost guaranteed they'd miss something. They might remember standard digits, but forget the formal uppercase Chinese numerals used in banking.
Right, which show up in historical texts all the time. Or they might just mistype a code. Suddenly your chapter parser reads a character perfectly, but your volume parser completely ignores it.
That would be a nightmare to debug.
Total nightmare. By creating a single source of truth, they eliminate the possibility of a contradiction. If they find a weird edge case character months later, they just update that one central function.
And the whole system instantly inherits the fix.
Exactly. It's the ultimate implementation of the DRY principle. Don't repeat yourself.
Don't repeat yourself, which is a huge concept in software architecture. You never want the same core logic existing in two places.
Never.
But this is what's so fascinating, because of how they actually finished the volume parser after following this DRY principle.
Right. This is where the theory meets the somewhat unglamorous reality of programming.
Yes, because here is where it gets really interesting for you listening. We are talking about advanced Haskell programming.
Yeah.
And the source states that after extracting this crucial function, the rest of the implementation was, and I'm quoting here, merely copy and paste based on the implement of parsing chapter header.
Merely copy and paste. It's just so refreshingly honest.
I love it. It totally shatters that Hollywood myth of software engineering. We picture a master programmer typing out bespoke algorithms all night. But the reality is, once the complex variable was isolated, the solution was basically Control-C, Control-V.
Which naturally raises a big question about best practices.
Yeah.
If the rule is don't repeat yourself, isn't copying and pasting code doing exactly that?
That's the tension. On the surface, it feels super brittle, like you're creating technical debt.
Okay.
If you copy a whole chunk of logic and there's a bug in it...
You've just cloned the bug.
Exactly. So how is this good design?
Well, we have to distinguish between duplicating the complex logic and duplicating the structural scaffolding.
Okay, unpack that for me.
In this parser, the volatile complex logic was identifying those numerals. The surrounding structure, the part that says, look for a keyword, find a space, find a token, that scaffolding is highly stable.
Ah, because a volume header structurally behaves exactly like a chapter header. They're both just signposts.
Yes. And in the strictly typed language, if two concepts share the exact same structural behavior, trying to write one overly clever, generalized function for both can actually backfire.
It makes the code too tangled.
Exactly. It gets harder to read and maintain. Sometimes duplicating that simple boilerplate structure is the most pragmatic choice, as long as the dangerous logic is abstracted away.
So the copy and paste isn't laziness. It's actually proof that the original architecture was sound.
It absolutely is validation. Think about it. If you can copy a complex routine, change the keyword from chapter to volume, and have it work flawlessly on the first try,
That's amazing.
it means the original developer wrote incredibly clean, decoupled code. It was a perfectly modular component.
It's like taking a blueprint for a really well-designed apartment. You don't redraw the load-bearing walls just because you're building the second floor.
That's a perfect way to look at it.
If the layout works, you duplicate the layout. But You make sure both apartments draw water from the exact same main water line.
And the water line is Chinese numeral or digit function.
Exactly. You duplicate the empty rooms, but you share the utility. It is just a masterclass in separating the what from the how.
And there's another really interesting software principle at play here. It's called the rule of three.
The rule of three.
Yeah, a lot of experienced developers argue you shouldn't try to abstract code the very first time you write it, because you don't fully understand how it'll be used yet.
Oh, premature abstraction.
Right. It leads to overly complex systems.
You end up building a giant multi-tool when all you actually needed was a hammer.
Exactly. So you write the chapter parser first, and you let the numeral logic live locally. It's only when the second requirement comes along, the volume parser, that the pattern becomes clear.
The developer realizes, oh, I have two structures that need the exact same logic.
And that is the precise, correct moment to extract the function. They waited until the system practically demanded it.
That is such an elegant approach. Let the necessity dictate the architecture, rather than trying to predict the future. It completely reframes this whole snippet.
It really does.
We started with what looked like a tiny, trivial update, but we're actually looking at a pristine example of software evolution.
We are seeing the exact moment a system matures. It transitions from that flat sequence into a hierarchical tree. It abstracts universal laws and relies on proven duplication instead of inventing unnecessary complexity.
It just highlights the hidden craftsmanship behind our digital infrastructure. The tools that run our world, they aren't held together by chaotic reinvention. They're held together by careful categorization and reusing stable patterns.
And trusting the compiler to enforce the rules.
Yeah. When a developer hits copy and paste, they aren't always taking a shortcut. Often, they're leveraging the stability of their own foundation.
Exact.
It's a great takeaway. But before we wrap up this deep dive, there's one final, somewhat provocative thought I want to leave you with, based on everything we just discussed.
No, lay it on me.
It has to do with the fragility of these foundational assumptions, the blind spots of the machine, if you will.
Blind spots. Okay.
So we know this system's newfound elegance relies entirely on that abstracted function. The parser is beautifully optimized to catch standard digits and Chinese characters.
It's a finely tuned net.
Exactly. But what happens to this whole flawlessly copy-pasted structural hierarchy if the fundamental nature of the input text suddenly changes?
Like if the format introduces a pattern the universal function isn't looking for.
Right. What if the source material suddenly switches to Roman numerals? You get a manuscript that says Volume 4, Chapter 9.
Oh, wow. The entire parser would just go blind.
Yes, because it is now universally dependent on that single function to define a number. It would read right past the IV and the IX, because to the machine, those are just alphabetical letters.
The structural boxes would stay entirely empty because the tokenizing line never recognized the materials.
And that is the ultimate paradox of highly optimized systems. The more perfectly tuned your tools are for a specific environment, the more vulnerable the whole architecture becomes to the unknown.
That shared logic is exactly what causes it to fail globally.
Precisely. So as you navigate the complex systems in your own life, digital or otherwise, ask yourself, how resilient is this structure, really? And what happens when the very definition of the data it relies on suddenly changes? Just a little something to chew on the next time you encounter a flawless system.
Definitely food for thought.
Absolutely. Well, thanks for joining us on this deep dive, and we'll catch you next time.